This is a monorail train invented in Britain over a century ago. It can automatically adjust its position to maintain balance on a single track without a driver's control, seemingly defying the laws of physics. But how does it actually work? In the early 1900s, British inventor Brennan aimed to solve the high cost of laying traditional dual-track railways and the difficulty of adapting to curved routes due to large turning radii. Using the principle of gyroscopic angular momentum conservation, he invented a monorail train capable of automatically correcting its tilt angle. Initially, he discovered that when a gyroscope's rotor spins rapidly, the angular momentum it generates helps it remain stable. If external forces cause it to tilt, the spinning disc rotates around the vertical axis, a phenomenon known as gyroscopic precession. This means that no matter how external forces act, the gyroscope can always rely on the law of angular momentum conservation to return to its original balanced state. Brennan installed a small flywheel in a model train, connecting it to a motor for experiments. Although the gyroscope's precession effect helped stabilize the train, the problem arose when the train encountered a turn. Since the gyroscope itself didn't rotate with the train, and precession prevented the train from turning, it eventually tilted and derailed. To solve this issue, Brennan added a second gyroscope, spinning in the opposite direction and connected by a set of gears. When one gyroscope tilted, the other would rotate in the exact opposite direction. This allowed the two gyroscopes to counteract excessive precession during turns, keeping the train stable. After overcoming technical hurdles, Brennan decided to build a full-scale prototype. It was large and heavy, equipped with two giant gyroscopes spinning at high speeds. But at this stage, he realized that unlike small-scale models, the gyroscopes not only had to counteract their own rotation, but also had to resist the massive gravitational force acting on the train itself. When the train tilted, its center of gravity would pull it downward. If the gyroscope couldn't generate enough precession force, it wouldn't be able to keep the train stable. To increase the gyroscope's precession force, Brennan connected it to a gasoline engine and placed it in a vacuum-sealed casing to reduce friction. Even if power was lost, the gyroscope could continue spinning for a long period, ensuring the train wouldn't tip over immediately. Brennan then mounted the gyroscope on a universal joint, allowing the entire system to rotate along the train's lateral axis. He extended each gyroscope's rotation axis outside its casing, adding guide plates connected to the train's chassis on both the top and bottom. When the train tilted, the gyroscope's rotation axis would contact one of the guide plates. The friction generated would cause the gyroscope to roll on the plate, significantly amplifying the precession force and keeping the train balanced. But this introduced a new problem. Vibrations from the moving train caused the gyroscope's rotation axis to repeatedly bounce on the guide plates, making it difficult to generate a stable and appropriate torque. Brennan ultimately abandoned the guide plate system and adopted a more refined design. He fixed the gyroscopes beneath the train, allowing them to rotate with the train itself to naturally generate precession force. At the same time, a control rod was installed on the right side gyroscope's rotation axis, connected to a lever system that controlled an air valve. When compressed air was released, a gear rack was placed between the two gyroscopes. The moment the train tilted, the gyroscope would produce precession, driving the control rod to push the air valve open. The compressed air would then flow through one of the pipes into a larger chamber, and the pressure would force the second gyroscope to produce counter-precession, restoring the train's balance. This entire process happened almost instantly, and it cleverly utilized mechanical power to amplify a small force into a larger force, absorbing the train's gravitational tilt. Even if all passengers stood on one side, the train would not tip over. Although Brennan's prototype was a massive success, it failed to attract investors. Each train car required a complex gyroscope system, increasing costs and adding various uncertainties. Additionally, traditional dual-track trains were already highly developed at the time, leading to the project's abandonment. However, this principle later became crucial in the field of aerospace technology. It just goes to show, human ingenuity is truly limitless.